Testing? Oh, cool.
It works. So here is Travis Goodspeed. This talk was not prepared. I mean, it was not supposed to be in the schedule, but he wanted to make a talk, so you're welcome. He will be talking about some magic tricks in MIPS assembly.
Oh, howdy. Okay, so there are no slides for this talk, but if you want to repeat the trick afterward, you can find it written as a paper in Proof of Concept to Get the Fuck Out 15. We're all reverse engineers here, and we take things apart, but sometimes it's also fun to fuck with reverse engineers. You know, when you have code and you're reversing it, it would be nice to be able to write code that will not work in an emulator and will not read correctly in disassembly. So in the MIPS architecture, there's this feature called a branch delay slot. MIPS was designed in an era when they were really optimistic, and they thought that they could remove all of the complexity from the chip and make it the compiler writer's problem. So MIPS has a pipeline that used to have like 2 stages, and then it was 5. Modern MIPS chips have on the order of like an 18-stage pipeline, 2 of which are optional. And this pipeline allows multiple instructions to run at the same time. So when you write your assembly in order, the CPU is actually queuing these up and doing pieces of each instruction in parallel until it hits a branch when it flushes that pipeline to replace the instructions with new ones. It's a little bit of a waste that these almost executed instructions that are already queued up in the pipeline get flushed away. But that's necessary whenever the branch prediction is wrong. And that's also necessary whenever like, the CPU changes to doing something else, like a mode switch or that sort of a thing. So the designers came up with a simple rule. They said whenever there is a branch, such as a function call or a return, we're going to execute the very next instruction after that branch or return. So when you're reading MIPS code or Spark code, you'll see in your reverse engineering tool that the function doesn't end on the last instruction. It doesn't end on the return. It actually includes the very next instruction after that. Now, the compiler will only insert an instruction there if it's actually going to be executed. So as a reverse engineer, or as a student reading the Patterson and Hennessy books on computer architecture, you are taught that the instruction after the branch is executed. And that's how I explained the rule to you earlier. That's not quite true, though. What actually happens is that the pipeline stage after the return is allowed to finish executing because it's already done everything but write its results back into the registers. And this is a slightly different thing. So you can abuse the difference between the rule of thumb, which is that the next instruction is executed, and the physical behavior, which is that the next pipeline stage is allowed to complete execution. The way that you can abuse this is you can put in an instruction which has a hazard. A hazard is when 2 adjacent instructions use the same registers. The return instruction on MIPS uses the program counter and the link register. So if you have anything that depends upon their values, the CPU will push it backward 1 pipeline stage and place like a no-op bubble in between them. So what you can do is, in regular 32-bit MIPS code, you can put 2 returns at the end of each function. And if you have 2 returns on a physical MIPS chip, what will happen is that at the end of the function, it hits the return, and then on physical hardware, the second return instruction is pushed back a little bit, and there's a bubble placed in between. So it's the bubble that's allowed to finish executing instead of the second return instruction. On QEMU, it doesn't behave that way. On QEMU, because instructions are emulated in order, and there's no concept of a pipeline, QEMU will always execute that instruction after the branch, even if it has a pipeline hazard. So by simply doubling up the return at the end of every function, wherever you see a function ending with a no-op, you can just replace that with another return. That will break compatibility with QEMU. Unfortunately, it does this by crashing, and what you'd rather have happen is that you could discreetly, sneakily identify that you're running on an emulator without crashing your program or triggering a fault or an illegal instruction. So the way that you can do that is that MIPS chips, like ARM chips, have two different instruction sets. They have regular MIPS, which is called MIPS 32 now, and they also have an abbreviated form of MIPS called MIPS 16. MIPS 16 is like thumb to ARM. And just like ARM and thumb, and unlike the shortened form of PowerPC, the least significant bit of your program counter determines which instruction set you're using. So if you branch to an odd address, if you call an odd function pointer, then you execute the code at that address in MIPS 16 mode. And an even address will execute that code in MIPS 32 mode. So in MIPS 16, which is also a RISC instruction set, you have fixed width 16-bit instructions, which are variable width. What I mean by this is that even though your assembler or your disassembler will tell you that say a branch, for example, is 2 instruction words long, that it's 32 bits wide instead of 16, it's actually 2 16-bit instructions that are next to each other. And the way that it works physically is that the first instruction hangs around in the instruction decoder to change the meaning of the instruction that comes after it. So, for example, if you have an add immediate extended instruction, this adds some immediate bits to a register. And the extended part means that the first word contains additional immediate bits that are added onto your result. Physically, what happens is that the first instruction hangs around in the instruction decoder and allows a bubble to move forward in the pipeline, so that when the second instruction arrives in the instruction decoder, its meaning is changed. Now, if you put one of these wide instructions into the branch delay slot, what happens? Well, on physical hardware, the instruction decoder takes the first word, allows a bubble to move forward as it changes the word that comes after. So when this is in a branch delay slot, in physical hardware, only the bubble is executed. In QEMU and in IDA Pro, since we like to bash IDA Pro here, because it's disassembling each instruction, and because all disassembler writers learned on x86, where it's completely natural to have a variable width instruction, QEMU will believe that the wide instruction is the final word of the function, when in fact it's completely ignored. So if you take an add immediate extended instruction at the end to add just 1 to your return register, and you have a return instruction before that, you have a 6-byte function that will return its first parameter on real hardware, or 1 more than that on an emulator. So you can write MIPS code using these tricks that will do whatever malicious function you like inside of, say, a home router. But when you try and take that same code and load it up in QEMU in order to trace it and debug it and reverse engineer it, it can have completely different behavior. Isn't that nifty? So, whenever you have these weird effects inside of physical hardware, that emulators don't need to get right in order to run code as is produced by compilers. You wind up with little edge cases that you can abuse. In the case of MIPS 16, MIPS 16 existed as an instruction set for quite a while before Linux distributions like OpenWRT would ever compile with it, because the compilers weren't reliable enough. And unlike MIPS 32, where the compilers regularly put an instruction into the branch delay slot, MIPS 16 compiler will almost always leave them as no-ops, because it's not confident enough that they will work. You can also use these exposed pipeline tricks in order to make code that runs on one revision of a chip, but not on another. So you can use them to, say, make code that will run on a Lungsun MIPS chip from China, but not the Imagination Technologies MIPS chips that are designed in the West. So that's a nifty little trick, and I thought I would share it with you. Thank you kindly.
Thanks. Do you have any question?
I have a question. If someone could please get me a bucket about this big and enough ice to fill the bucket to the top and enough water to wet the ice, and I also need a ½ kilogram of salt and one of these bottles of beer from the front. I would appreciate that very much. Thank you.